Hello student, good morning. I am Dr. K.Sinha, Professor of Chemistry. Today I will continue from the last class. Actually I am discussing states of matter, gaseous state. In that I have discussed about Charles' law and Boyle's law. Also I have discussed different values of R, gas constant. Now I am going to discuss further Dalton's law of partial pressure. Actually I am reviewing the entire chapter of gaseous state part 1. Now I am going ahead. Dalton's law of partial pressure. If two or more gases which do not react chemically are enclosed in a vessel, then the total pressure exerted by the gaseous mixture is equal to the sum of all the partial pressures that each gas would extend when present alone in the same vessel at the same temperature. Again I am telling you Dalton's law of partial pressure. If two or more gases which do not react chemically are enclosed in a vessel, then the total pressure exerted by the gaseous mixture is equal to the sum of all the partial pressures that each gas would exert when present alone in the same vessel at the same temperature. Mathematically, P is equal to a small p1 plus a small p2 plus a small p3. Here P denotes pressure. Capital P means total pressure. A small p means partial pressure. Suppose three gases were there, then each gas will have some pressure. That is a small p1, a small p2 and a small p3. Then total pressure P will be a small p1 plus a small p2 plus a small p3. If it is more, then plus like that way. Now aqueous tension. What is the aqueous tension? The pressure exerted by the water vapors at a particular temperature is called aqueous tension at that temperature. It depends only on temperature. Aqueous tension, again I am telling you, aqueous tension is the pressure. It is the pressure exerted by the water vapor at a particular temperature is called aqueous tension at that temperature. It depends only on temperature. Now, how will you calculate pressure of a dry gas from that of the moist gas? That I am telling you. Calculation of pressure of a dry gas from that of the moist gas. When a gas is collected over water at T degree centigrade, it is moist. According to Dalton's law of partial pressures, P moist, pressure of moist gas, is equal to pressure of dry gas plus aqueous tension at T degree centigrade. Pressure of moist gas includes pressure of dry gas plus aqueous tension at the same temperature. Hence, pressure of dry gas will be pressure of moist gas minus aqueous tension at same temperature, that is the T degree centigrade. Because P moist gas is equal to P dry gas plus aqueous tension at T degree centigrade in same temperature. Then pressure of dry gas is equal to pressure of moist gas minus aqueous tension at the same temperature, that is the T degree centigrade. Now next term I am going to discuss Graham's law of diffusion. Under similar condition of temperature and pressure, the rates of diffusion of different gases are inversely proportional to the square root of their densities. Again I am telling you, under similar condition of temperature and pressure, the rates of diffusion of different gases are inversely proportional to the square root of their densities. Mathematically, we can write R1 divided by R2, a small r1 divided by a small r2. R means rate. R means rate of diffusion. Then R1 upon R2 is equal to under root d2 upon d1. Here d means density. A small d2 upon a small d1. R1 upon R2 is equal to under root d2 upon d1. That is equal to under root m2 upon m1. Here m is the molecular mass, capital M. m2 upon m1. Here you should know that mass is equal to, molecular mass is equal to 2 into vapor density. Don't forget. Here mass is equal to 2 into vapor density. That's why d2 upon d1, then density you are knowing, then that you can write in term of mass, molecular mass, because molecular mass is equal to 2 into vapor density. Means 2 into d2 upon 2 into d1. Then now you have multiplied by 2 up and down. But 2 into d means density, that is the molecular mass. That's why you can write that is the R1 upon R2, that is under root d2 upon d1, that is equal to under root m2 upon m1. Now this actually what I told you, that is the Graham's law of diffusion. Now only rate of diffusion. Then rate of diffusion is equal to volume of gas diffused divided by time taken. Rate of diffusion is equal to volume of gas diffused divided by time taken. Okay. That is the, suppose volume is capital B, time taken is a small t, then R is equal to V upon T. Hence you can write V1 upon T1, that is equal to V2 upon T2, that is equal to under root D2 upon D1. Correct? Rate is equal to V upon T, volume divided by time. Then you have written R1 upon R2, Graham's law of diffusion. There now you can write in the place of R1, you can write V1 upon T1 and R2 is equal to V2 upon T2, and that is equal to under root D2 upon D1. Now for the volumes diffused in the same time, that is when T1 is equal to T2, in that situation what will be the rate of diffusion? Then now here T1 is equal to T2, both are equal. Then for the volumes diffused in the same time, you can write V1 upon V2 is equal to under root D2 upon D1, that is equal to under root M2 upon M1. In Gram's law, simply in the place of R1 and R2, R1 means now V1 upon T1 and R2 is equal to V2 upon T2. Here T1 and T2 is equal. If T1 and T2 is equal, then for the same volume, not same volume, here for the volume diffused in the same time, means T1 is equal to T2. When T1 and T2 both are equal, that time volumes diffused in the same time, then in the formula T1 is equal to T2, then T1 and T2 both will be cancelled. Okay, then what will remain? V1 upon V2. All things will be the same. V1 is equal to V2 is equal to under root D2 upon D1, that is equal to under root M2 upon M1. Here T1 is equal to T2. For the diffusion of same volume of two gases, if V1 and V2 both are same, then in that situation, that V1 and V2 will be cancelled out, V1 upon T1 divided by V2 upon T2. Now here V1 and V2 is equal to equal. V1 is equal to V2. Then what you will get? T2 upon T1. T2 upon T1. Because V1 and V2 will be cancelled out. V1 upon T1 divided by V2 upon T2. Then it will reverse. Then V2 will cancelled. Then what will remain? T2 upon T1. All things will be the same. Then T2 upon T1 is equal to under root D2 upon D1, that is equal to under root M2 upon M1. Actually, this formula will be useful while solving the numericals. Same time you have to calculate time of diffusion. Sometimes you can say if time is the same, the what will be the volume of two gases diffused. That time this relation will be useful. Now next point I am discussing, that is the difference between diffusion and effusion. Question is asked. Difference between diffusion and effusion. 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 Diffusion means DIFFUSION. Diffusion. And here is effusion. Then what are the difference between diffusion and effusion? Now I am telling you. Diffusion refers to the spreading of gas throughout the space or into a second gas or substance, whereas here diffusion, I told you, diffusion refers to the spreading of gas throughout the space or into a second gas or substance. Whereas effusion, what is the effusion? Effusion refers to the escape of gas through an orifice, that is a tiny hole, TINY, tiny hole or tiny hole. Means suppose balloon is there and that balloon is in that air is there, right? And suppose one hole is there, you have made one hole, that is called orifice. Then gas will come out. Then that time gas will escape from the hole, that is called effusion. Effusion refers to the escape of gas through an orifice, means a tiny hole. Correct? And diffusion refers to the spreading, simply a spreading of gas throughout the space or mixing of gas into a second gas or substance. Now I am going to discuss postulates of kinetic theory of gases. Very, very important. Postulates of kinetic theory of gases. Many question is asked. Hence listen carefully. First point, there are total 8 points. 8 points. You listen carefully. Postulates of kinetic theory of gases. First point, every gas is made up of a large number of extremely small particles, and that small particles is called molecule. Every gas is made up of a large number of extremely small particles called molecules. All the molecules of a particular gas are identical in mass and size and differ in these from gas to gas. Suppose only one gas is there, then all the molecules of a particular gas are identical in mass and size and differ in these from gas to gas. If different gases are there, then their mass and size will differ. If same gas is there, then mass and size will be the same, means identical. Now, second point. The molecules of a gas are separated from each other by large distance, so that the actual volume of the molecules is negligible as compared to the total volume of the gas. This is the important point. Again you listen. The molecules of a gas are separated from each other by a large distance, so that the actual volume of the molecules, molecules is negligible as compared to the total volume of the gas. Third point, the distance of separation between the molecules are so large that the forces of attraction or repulsion between them are negligible, because separation between the molecules are very large, correct? So that the force of attraction or repulsion between them are negligible. Now, fourth point, the force of gravitation on the molecules is also supposed to be negligible. Correct? This is again important point. Question is asked. Listen carefully. The force of gravitation on the molecules is also supposed to be negligible. Now, fifth point. The molecules are supposed to be moving continuously in different direction with different velocities. You remember, in different direction with different velocities. The molecules are supposed to be moving continuously in different directions with different velocities. Hence, they keep on colliding with one another. This is called molecular collisions. Then they themselves, hence they keep on colliding with one another, as well as on the walls of the containing vessel. Means they will collide on the walls of container also, in which these gases are kept. Now, next point, sixth point. Because of collision on the wall, molecules will collide on the wall. That creates pressure. That is the sixth point. The pressure exerted on the walls of the containing vessel is due to the bombardment of the molecules on the wall of the containing vessel. Now, next point, seventh point. The molecules are supposed to be perfectly elastic. The molecules are supposed to be perfectly elastic hard sphere. Perfectly elastic hard spheres. Molecules are behaving like perfectly elastic hard spheres so that no energy is wasted when the molecules collide with one another or with the walls of the vessel. Means after collision there will be no wastage of energy. The energy may, however, be transferred from some molecules to the other on collision. On collision, energy may be transferred from from some molecules to the other on collision. This is the 7th point. And now last point 8th, I am telling you. Since the molecules are moving with different velocities, they possess different kinetic energy. You remember, since the molecules are moving with different velocities, it means they possess different kinetic energy. However, the kinetic energy of the molecules of a gas is directly proportional to the absolute temperature of the gas. Correct? Then today I am stopping only here. Next class again I will continue. Thank you.